In this video, I'm going to walk you through a couple of examples of calculating the pH of ionic compounds. The first example that we're looking at is a solution of 0.075 molar KCN, and we've been provided with the Ka value of HCN, which is going to be relevant to this problem, even though we are using KCN. The very first thing that we should be doing here is writing a balanced equation for the dissociation of the KCN compound. When the KCN compound is put into water, it's going to dissociate into its cation, potassium, and its anion, cyanide. And let's just make a little ice table to help us make some predictions about that dissociation. If we are starting initially with 0.075 molar KCN, prior to dissociation, we don't have any product yet. The KCN molecule is going to totally dissociate in the solution, so all 0.075 of that solution is going to dissociate, and we're going to make 0.075 K plus ion and 0.075 molar cyanide ion. And this relationship 1 to 1 to 1 is coming from the stoichiometric coefficients of this equation. So at the end, when this is done dissociating, we will not have any more KCN. We'll have 0.075 molar potassium ion, and we'll have 0.075 molar cyanide ion. Of these two ions, we need to now figure out which one of them is going to be controlling the pH of this solution. The potassium ion, because it's in group 1A, this is a neutral cation. The cyanide ion is not one of those five the 5 neutral anions, which means that the cyanide ion is basic. Because the potassium ion is neutral, it is not going to be controlling the pH of the solution at all, and we don't need to be thinking anymore about the potassium ion. We can ignore it from here on out. The cyanide ion we have determined is, because it's basic, it is what will be controlling the pH of this solution. So now we want to think about this question a little bit different. We want to think about this question as calculate the pH of a 0.075 molar cyanide ion solution, since that is the basic component. So now that we've kind of reconfigured what this problem is asking us to do, now we need to write an acid-base reaction for the cyanide ion. In this reaction, just like all the ones that we've done previously, we want to write this balanced equation for the cyanide ion reacting with water. Cyanide ion is a weak base, so that means, first of all, that it's going to be in equilibrium, and second of all, that it's going to be producing HCN, because the cyanide as a base is going to be taking one of the hydrogens from water. So it's going to make HCN, and it's going to make OH minus. And the amount of OH minus that it makes is actually what's going to control the pH of this solution. So this should feel a lot like just kind of solving a weak base pH calculation problem. The initial amount of the cyanide ion is the 0.075 molar. That's how much we're starting with here. Prior to the cyanide ion reacting with water, we don't have any of our products at all. Because this is a weak base, we don't know exactly how much cyanide is going to react, so this is where we use our X variable, because we don't know how much of that cyanide ion is actually reacting, and we don't know exactly how much HCN and OH minus we're producing. Once we get into equilibrium, we're going to have 0.075 minus X of the cyanide ion, and we're assuming that X is a really, really small number, and it's just going to be about 0.075. The HCN is X and the OH minus is X. And again, what we want to know is the value of this OH minus. The value of the OH minus is ultimately what controls the pH. To solve for that X, we're going to write an equilibrium expression. This equilibrium expression is a Kb. I know that it's a Kb because we're dealing with a basic anion, which we've classified over here. So this is a Kb. The Kb is going to be HCN, our product, HCN, times our other product, OH minus, over cyanide, Cn minus. Remember, we leave water out because it's a pure liquid. And we can plug in X and X for the HCN and for the OH minus, so that gives us X squared, and 0.075 as our cyanide value. All that we need to know is the Kb. Let's go all the way back to the beginning of the problem. The problem gave us the Ka of HCN. It didn't give us the Kb. but we have learned that there is a relationship between Ka and Kb of a conjugate acid and a conjugate base. So for a conjugate acid-base pair, the Ka times the Kb is Kw. So that means the Kb, which is what we need to know, is the Kw divided by the Ka. Kw is 1 times 10 to the minus 14, and the Ka for this problem is 4.9 times 10 to the minus 10. So the Kb that we're looking for here is going to be 2.04 times 10 to the minus 5. And we can take that down and plug that in. And now we just need to solve for x. So working on this equation right here, this math equation right here, when we solve for x is 0.00124. And remember that x represents the OH minus concentration in our ice table, which means that we can use x to calculate the pOH. The pOH is the negative log of the OH minus concentration. For us, this is 0.00124. The pOH of this solution is 2.91. The pH is 11.09. Just as a reminder, the pH plus the pOH is always 14. The pH, 11.09, plus the pOH, 2.91, is going to be 14. Let's take a look at another one of these problems. This one is going to be pretty similar. We have calculating again the pH of a 0.93 molar solution, and we're giving a pKb, which is a little bit, I think that might be a little bit new, but we'll talk about what that represents. So first of all, we need to write a balanced equation that shows the dissociation of our ionic compound once it is placed into water, C6H5NH3 plus and Cl minus. We're going to make a little ice table for this, starting with 0.93 molar of C6H5NH3Cl. Initially, we have no products. This completely dissociates, leaving us with 0.93 of both of our products. Next step is to determine which of these products is acidic or basic. When we're looking at our cation, this is not from group 1A or group 2A, so this is an acidic cation. Our anion is one of those 5 neutral anions, so this is a neutral anion. So from here on out, we're going to be focusing on the C6H5NH3 plus ion because it is acidic. It's what's dictating the pH of the solution. Next job is to take that C6H5NH3 plus and write a balanced equation with it reacting with water as a weak acid. Acid because it's acidic. As an acid, that means that it is going to be losing one of its many hydrogens. I'm going to take it from the end of the molecule. So it's going to be C6H5NH2 plus H3O plus. The H3O plus concentration is what will dictate the pH of the solution. Let's make this ice table starting with 0.93 molar C6H5NH3 plus. No products initially. We don't know how much of this will react because it is a weak acid and it's in equilibrium, but we know in equilibrium that we'll have approximately 0.93 molars of our C6H5NH3 plus, and we'll have X of each of our products. Next, we're going to write an equilibrium expression. This equilibrium expression is a Ka. It's a Ka because this is acidic. We determined that this is acidic. The Ka is going to be our products, x squared, over our reactant, 0.93. So we just need to figure out what the Ka is. We were given the pKb. You might not be familiar with the pKb, the concept of pKb. pKb and pKa is kind of like pH or pOH. So the pKb is going to be the negative log of the Kb, just like pOH is the negative log of OH. pKa would be the negative log of the Ka. Also, like pH and pOH, the pKb plus the pKa for a conjugate acid-base pair is going to be 14. That's pretty handy. So we need to know what the Ka is, and we're starting with the pKb. So why don't we begin by figuring out what the pKa is? We'll use this equation first. We'll figure out what the pKa is, and then we'll use this equation to get ourselves to the Ka. So we're going to say the pKa is 14 minus the pKb. For this problem, that's 14 minus 4.87. The pKa is 9.13. And now that we know the pKa, let's use our regular properties of pKa, just like pH or pOH. If the pKa is the negative log of the Ka, that means that Ka is 10 to the negative pKa. The same way that if we were trying to calculate H3O plus from the pH, we would say the H3O plus is 10 to the negative pH. Ka in this case is 10 to the negative 9.13. And we can just use it in that term in this equation. We don't have to actually do the math on 10 to the negative 9.13 as some sort of separate math equation. So now that we have this math equation set up, we can go ahead and solve for x. We'll do some algebra here. We'll multiply these two terms by each other and then take the square root. Again, this is a lot like calculating the pH of a weak acid. X works out to be 2.63 times 10 to the minus 5. Let's take a look at what x represents in this equation. X represents H3O plus. So that means that we can plug this directly into the pH equation. Negative log of x. I'm just going to put the value right in there. The negative log of 2.63 times 10 to the minus 5. And that is a pH of 4.58.